My name is Erin Bugbee, and I am a PhD student at Carnegie Mellon in the Department of Social and Decision Sciences. And today I'll be walking you through my poster from our CogSci 2024 paper titled Feedback Promotes Learning and Knowledge of the Distribution of Values Hinders Exploration and an Optimal Stopping Task. This is joint work with my doctoral advisor, Bugbee Gonzalez. In many naturalistic settings, such as deciding on an apartment to rent or when selecting a life partner, people often explore options before making a selection. In this work, we investigate the following. How do feedback and knowledge of the distribution of option values affect learning in sequential search? And how do people deviate from optimal based on these factors? Can this be modeled with a cognitive model of decisions from experience? Previous work indicates that people are suboptimal at stopping exploration in these types of problems. They often stop earlier than optimal, conclude their search too early. However, recent work has indicated that people may learn to stop at the optimal point with experience. In our work, we investigate factors that may influence learning and stopping decisions, and extend our previous modeling work to this new task that we have developed. The data that we're looking at consists of 256 human participants from Amazon Mechanical Turk. We have a completely between subjects design where participants either are informed of the distribution of values or not. We call this known or unknown knowledge of the distribution. And they receive one of three types of feedback, either no feedback, outcome feedback in which they're informed of the correctness of their decisions, or detailed feedback in which they're informed both of the correctness and what they should have chosen. We also simulated 256 instance-based learning model agents, as well as 256 optimal agents for comparison to human behavior. And here's the task. Participants are shown boxes, shown on the right, with values inside of them. And these values are sampled from the distribution shown on the left. The participants are instructed to choose the box with the maximum value in a sequence. The sequence is all consisting of 10 boxes. So if they don't think it's the maximum, they pass and they continue doing that until they ultimately make a selection. And if they reach the last box in the sequence, box 10, they must select it. They do this for 50 rounds, and they're instructed that they want to maximize their total points, selecting the maximum on each of those rounds. In the known distribution condition, participants are informed of the distribution before beginning the task. So they are shown the distribution, it's also described to them, and they are forced to answer many questions about this to ensure that they understand it. In the unknown distribution condition, they do not go through this phase, and instead they begin the task directly. We have those three feedback conditions. In the no feedback condition, participants are told also the feedback only comes when they make a selection, not on the passes. So only once they've selected a box do they receive feedback. In the no feedback condition, they're told you chose this box with this value. They already know this. So this is essentially uninformative. In the outcome feedback condition, they're told whether their choice was correct or wrong. And in the detailed feedback condition, they're told both the correctness as well as what the maximum value box was and where it occurred in the sequence and what the value was. We develop an instance-based learning model in order to predict human behavior in this task. So we use these predictions to inform what we believed people would do in our hypotheses. I recommend checking out this reference if you'd like to learn more about instance-based learning theory. There's been over 20 years of work now on this theory and various models and how they have predicted human behavior accurately in a variety of domains, ranging from simple binary choice to cybersecurity. And I'll provide a brief summary of this theory here. So learning occurs through the accumulation of memory units called instances. Past instances are retrieved based on similarity to the current situation and frequency and recency. A blended value is calculated based on the utility of those retrieved instances, and then the agent chooses the option with the highest blended value. So these instances have a structure consisting of state, what is the context in the world, the action taken, and utility or feedback. Here the state is the value of the box and the number of boxes remaining. These are both told to participants. The action is either to select or pass on the box, and the utility is binary. And what that corresponds to varies by condition. So in the no feedback condition, the utility is 1 if the box chosen is the maximum value so far after the first box. This means we have some indication that this could in fact be the best, the highest valued box. In the outcome and detailed feedback condition, it is both 1 corresponds to correct and 0 corresponds to incorrect. For the detailed feedback condition, however, there are additional instances for that piece of information provided of what is the maximum valued box and where does it occur in the sequence. And this is what these instances look like. Now, getting into the results, we have the optimal decision makers shown in black and the human shown in red. This is over blocks of 10 problems, and we're looking at the accuracy here. What proportion of the time are the decision makers choosing the maximum valued box in the sequence? So to start, we see that accuracy is highest in the detailed condition compared to outcome, and higher in outcome compared to no feedback. So there definitely is an effect of feedback on how well people are doing at this task, and detailed seems to provide better, seems to lead to better accuracy than outcome feedback. We also see substantial improvements over time, over these blocks of problems, from the first block to the 5th block in both the feedback conditions. So feedback does seem to be improving learning. And then another finding that we see, which is a little bit more difficult to see in the figures here, but people are actually statistically doing searching longer when they do not know the distribution of values compared to when they know the distribution. And this actually helps them perform better. So since people tend to stop too early, when they don't know the distribution, they're actually encouraged to explore. And this leads them to stop closer to the optimal stopping point and actually do better than those in the known distribution condition. So this is a very interesting finding that we see. We also have the results from the IBL model. And so we see in blue the IBL model, and those predictions are very similar to what we see in the human behavior with learning over time, as well as improved accuracy for the feedback relative to no feedback conditions, and highest accuracy and detailed relative to outcome, and outcome relative to no feedback. Okay, so here are our key findings. First, feedback promotes learning. Participants in the feedback conditions stopped closer to the optimal position with experience and also achieved higher accuracy than when not receiving feedback. Knowledge of the distribution hinders exploration. So participants with that distribution knowledge actually explored less by stopping earlier than those without this knowledge, and that hindered both their exploration and their accuracy. And finally, the model predictive accuracy. The IBL model accurately predicted human stopping behavior across these conditions. In future work that we've already begun, we will investigate additional factors to better understand how these different environmental contexts affect human stopping decisions. This includes factors such as variability of sequence length and crowd decisions, for example. Here are the references from the poster, and finally, some additional information. First, our lab website, the DDM lab at Carnegie Mellon, my own personal website, and the QR code here will bring you to this video, the materials, the OSF with all of the code and scripts, and the paper, as well as this poster. Thank you so much for listening, and I hope you have a wonderful CogSci 2024.